1859 was a year of extreme solar activity. During September of that year, astronomer Richard Carrington was sketching sunspots when he observed an intensely bright event. Less than 18 hours later, auroras were seen around the world. They extended to low latitudes where the phenomenon is rarely seen. Telegraph operators across Europe and North America reported malfunctions, including electric shocks and sparking wires. This was the first time that solar storms had been linked with auroras and electrical and magnetic disturbances here on Earth, and it became known as the Carrington effect. Since the 1700s, a periodic fluctuation had been observed in the number of sunspots, but a deeper insight into the Sun's behavior would not emerge until 1958. James Van Allen was the chief scientist for America's first satellite, Explorer 1. It was equipped with a cosmic ray detector.
8, 7, 6, 5, 4, 3, 2, 1, firing command.
The launch was successful, but the orbit achieved was highly elliptical with an apogee far greater than expected. As its altitude changed, variation in the detector's readings suggested that charged particles were trapped in bands around the Earth. These became known as the Van Allen belts. It was a discovery with far-reaching implications. The energetic charged particles that make up the Van Allen belts emanate from the Sun and are trapped by the Earth's magnetic field. They fluctuate with solar activity, and they present a risk to spacecraft that have to pass through them. The previous year, physicist Eugene Parker, working at the University of Chicago, had predicted that a constant stream of charged particles would flow from the Sun. He called it the solar wind. The astronomical community was reluctant to accept this idea. Soon, his theory was vindicated, as early Russian and American spacecraft began detecting a constant stream of charged particles. Solar wind explained why a comet's tail always points away from the Sun. Parker's supersonic solar wind theory predicted a variable stream of plasma, charged particles, permeating the solar system. The Earth's magnetic field deflects most of the solar wind, preserving the Earth's atmosphere. In 1995, the Solar and Heliospheric Observatory was launched. SOHO monitors the Sun from a point where the gravity from Earth and from the Sun exert equal force, keeping the probe in a stable orbit. SOHO gives us a clear picture of the solar wind. Its LASCO instrument obscures the central disk of the Sun, revealing the corona, the Sun's atmosphere. The planets are also clearly visible. The horizontal lines flanking them are due to their brightness overwhelming the camera's sensor. SOHO's Extreme Ultraviolet Imaging Telescope was able to see waves traveling out from solar flares, causing snow-like interference in the image sensor. Solar radiation in the extreme ultraviolet varies from minute to minute and over the Sun's 11-year solar cycle. Solar activity generates tides in the Earth's atmosphere, which increase with altitude. This in turn adds to the drag felt by low-orbiting satellites. Communication systems can also be affected, in particular GPS services. Constantly monitoring the Sun's behavior is important, and in 2010 NASA launched the Solar Dynamics Observatory. It orbits the Earth geosynchronously at an inclination of 28 degrees, which gives it a constant view of the Sun. The SDO observes in a number of different wavelengths that correspond to different temperatures, each one revealing varying activities, from the surface to the corona and to the flaring regions. The Sun is not solid. Rather than rotating, it swirls. At the equator, it spins once every 25 days. At the poles, it takes 38 days. It's in a plasma state, extremely hot matter made up of loose electrons and ions. Plasmas are excellent conductors of electricity, and the movement of the Sun generates a tangle of magnetic field lines. The surface of the Sun, known as the photosphere, has a temperature of around 6,000 degrees Kelvin and is best viewed in the visible part of the spectrum. Here, sunspots appear as dark regions where magnetic flux impedes convection. These are about the size of the Earth. Beyond the visible spectrum, magnetic loops at the same areas become visible. The lower levels of the Sun's atmosphere, the chromosphere, see gravity yielding to the dynamic thermal and magnetic forces, with temperatures increasing to 8,000 degrees Kelvin. Ascending further through the solar atmosphere, a narrow band called the transition region sees temperatures rise to more than 500,000 degrees Kelvin. In the corona, seen here during an eclipse, it rises to 1,000,000 degrees Kelvin. Why this happens is not understood. The atmosphere is where the solar weather is generated. Solar flares appear as bright flashes, bursts of electromagnetic radiation from radio waves to gamma rays. Solar flares from some other stars are much larger than those from our Sun, and sometimes smaller stars, known as red dwarfs, display extreme solar flares. The SWIFT Gamma Ray Observatory is designed for rapidly locating brief bursts of gamma rays and X-rays. In April 2014, SWIFT saw a solar flare emanating from DGCVN. Its initial blast was 10,000 times stronger than any flare from the Sun. It was the first of 7 flares that continued for 2 weeks. DGCVN is a red dwarf, about 1/3 the size of the Sun, and it rotates twice as fast as the Sun. This enables it to generate a much stronger magnetic field. It's thought that the strength of the star's magnetic field is related to the intensity of the flares it emits. Coronal mass ejections are different. They are vast clouds of plasma blasted from the Sun's outer layers. They travel with the solar wind. While they are often linked with solar flares, researchers have not been able to establish a direct relationship. Observing the Sun in different wavelengths yields very accurate temperature readings, and the dramatic rise in temperatures moving away from the surface had scientists completely baffled. In 1990, a new spacecraft was launched.
Ignition and liftoff of Discovery and the Ulysses spacecraft bound for the polar regions of the Sun.
The Ulysses probe was bound for the Sun, but had to go the long way. Solar researchers wanted to have a different view of our star. The solar system coalesced from a vast cloud of gas and dust. As it collapsed, it began to spin, forming a disk. All the planets orbit along the plane of this disk, called the ecliptic. Ulysses would look at the poles, the parts of the Sun that could not be seen from our terrestrial viewpoint. Ulysses traveled via Jupiter, using the giant planet's strong gravitation to change its course. It approached on a path that took it over the planet's north pole. This bent the probe's trajectory beneath the ecliptic so that it could see the Sun from a polar orbit. From Ulysses, we learned that the Sun's magnetic field reverses every 11 years, and that the solar wind from the more dynamic South Pole was faster than from equatorial regions, yet the South Pole had no clear location. The only thing clear about the Sun was that it keeps changing. Now, heliophysicists wanted to be able to see the face of the Sun that was not seen from Earth.
Liftoff of the Delta II rocket with stereo, giving us a three-dimensional look at the physics of our Sun.
The twin stereo probes were launched in 2006. They were in slightly different orbits, one leading the Earth and moving slightly faster, the other trailing the Earth and moving slower. Each year, the two craft separated by 44 degrees, giving each an increasingly different view of the Sun. Because the Sun rotates, sunspots can develop out of sight. As sunspots are key indicators of solar weather, it's important to know just what is about to spin into view. The stereo probes now observe the Sun in 360 degrees. This makes it much easier to plot the direction of coronal mass ejections. Though these happen with reasonable frequency, most will miss the Earth. If they hit, they create havoc in electrical systems and trigger substorms in the planet's magnetosphere. Information provided by the stereo satellites is being used for the protection of power grids and satellites through regular space weather bulletins. Since the 1960s, observers had been aware that auroras would sometimes brighten suddenly, with movement within the auroral curtains increasing. These were short-term phenomena, quite distinct from solar storms that result in auroral activity lasting days. As communication satellites in geosynchronous orbits became more sophisticated, they registered sudden localized falls in the Earth's magnetic field that seemed to coincide with what were now being called substorms.
3, 2, 1. We have ignition and liftoff of a Delta II rocket carrying Themis, NASA's revolutionary journey to study the northern lights.
The Themis constellation of satellites was designed to monitor the behavior of the Earth's magnetosphere. The aim was to measure fluctuations within the Earth's magnetic field and relate any variations to changes detected in the auroras from ground stations in the North American Arctic. Each satellite was equipped with an array of booms to measure the strength and direction of electrical and magnetic fields. After several months, they maneuvered into elliptical orbits of varying eccentricity, with each reaching a high point above the night side of the Earth. The Earth's magnetic field deflects most of the plasma from the Sun. At times of high solar activity, some of the charged particles will spiral into the poles on Earth's day side. On the night side, the field lines are stretched to breaking point, called magnetic reconnection, when the plasma suddenly rebounds along the field lines into the polar regions. In February 2008, two of the probes detected a reconnection event, and 96 seconds later, the ground stations registered a sudden brightening of the aurora. The giant loops bursting from the Sun's surface are known as flux ropes. They are one of the most basic configurations in plasma. The glowing plasma follows helical magnetic field lines twisting around a central core. The Themis satellites discovered that flux ropes can extend all the way from the Sun to the Earth's upper atmosphere, carrying currents as high as 650,000 amps. Heliophysicists remained baffled by the behavior of the Sun's atmosphere, so a new probe was constructed. Known as IRIS, it was small and simple. It consisted of a telescope, an imaging spectrograph, and ancillary support equipment. It was cheap to build and cheap to launch. IRIS was placed in a polar orbit of the Earth that gave it an uninterrupted view of the Sun. It was able to look at the edge of the chromosphere where the plasma began its steep increase in temperature. Its images were far more detailed than had been delivered by any other probe and it could discern rapid changes. The waving jets of plasma, called spicules, were revealed in great clarity. There are roughly 10 million spicules across the Sun's surface at any given moment. They can grow to 10,000 kilometers, yet they collapse in 5 or 10 minutes. Researchers have made computer models of the spicules that behave in the same way as the images from Iris. It is thought that they form through the interaction of charged and neutral particles with the tangled magnetic fields. It seems magnetism must play an important role in the heating of the solar corona and in the high-speed ejection of plasma, but the mechanism is still not understood. There are at least 20 different satellites currently monitoring the Sun's behavior. Most are in orbit around the Earth. While it is important to get beyond the Earth's atmosphere to analyze the solar wind, it has not been possible to get really close to the Sun. Heliophysicists know the particles of the solar wind change not long after they leave the corona. If these particles could be sampled close to the Sun, it would reveal what part of the solar atmosphere was responsible for their extreme heat and their ultra-high speed. Until recently, it was not possible to build a craft capable of withstanding the temperatures in regions that scientists wish to explore. The team behind the Messenger probe to Mercury solved some of these problems with a woven ceramic sun shield which had to face the Sun at all times. Around 2010, work began on Solar Probe Plus, designed to pass the Sun just 6 million kilometers above its surface. A number of different systems have to work in concert to enable the probe to gather data inside the Sun's atmosphere. A carbon composite solar shield, surfaced with highly reflective alumina, will shade the rest of the craft from temperature extremes. As the Sun is a wideband radio source, the probe is out of contact during its close approaches and must function autonomously. In 2017, the probe was renamed the Parker Solar Probe, after Eugene Parker, the physicist who had first identified the solar wind. It was the first spacecraft to be named after a living person.
On a mission like this into new territory, you're going to be in for some surprises. Maybe not big ones, maybe only little ones, but you're going to find that your point of view will have to change to conform with the data. Why is the solar corona, the outer atmosphere of the Sun, at 1 million or 2 degrees when the Sun itself is only 5,600? It isn't because of sunshine, that's for sure. Again, we don't know until we make the flight and have a year or two to think about the data.
The Parker probe's launch weight is less than 700 kilograms, which is quite modest. Yet its launch vehicle, the Delta IV Heavy, is one of the most powerful boosters available.
Minus 15.
In the pre-dawn hours of August the 12th, 2018,
10,
the final countdown
9,
was proceeding.
8, 7,
Eugene Parker
6,
was at Cape Canaveral to
5,
watch the launch.
4, 3, 2, 1.
There we go.
The probe was headed for 26 highly elliptical solar orbits over 7 years. During its mission, it will make 7 close passes of Venus, slowing each time to sweep closer and closer to the Sun. After separation from its upper stage, the probe first deployed its solar panels. These fold back near the Sun, with a cooling system enabling them to survive. The magnetometer boom unfolded at the rear of the craft, and then the field antennae, to measure electric and magnetic fields and waves, snapped into place. Though the Parker probe leaves Earth at high speed, it uses Venus's gravity to slow down, allowing it to approach the Sun at the appropriate angle. However, as it falls toward the Sun, it will accelerate to 720,000 kilometers per hour. On its outward loops, it will lose speed. But as the mission progresses, the Parker probe will make closer passes at higher speeds. It made its first close approach of Venus after just 52 days. 1 month later, Parker approached the Sun. For 11 days, it was out of contact with mission control, quietly recording data while carefully keeping its sun shield pointed directly at the Sun. Though the heat in this region is extreme, the particle density is not. The sun shield will reach around 1,500 degrees Kelvin, and the protected electronics of the spacecraft will be at room temperature. As the probe loops away from the Sun, it's able to re-establish radio contact and play back the stored data. This is the first image from inside the Sun's corona, taken during Parker's first pass. It shows a coronal streamer. The bright spot is the planet Mercury. The dark spots are image correction artifacts. The Parker probe's second and third passes were at much the same distance and speed as the first, but subsequent passes will be both lower and faster as it continues to use Venus to modify its orbit. In 2024, the Parker Solar Probe will visit Venus for the last time, and its final 5 passes of the Sun will come down to 6.2 million kilometers from the surface. By this time, we should have a clearer understanding of the processes that heat the solar wind and expel it at such high speeds. But whatever we learn about our Sun, it will raise new questions. A clearer understanding of the Sun has led to design changes in satellites and revised management practices of power grids and communication systems. But with new proposals to send humans back to the Moon or on planetary expeditions, we will need to understand more about the potentially hostile solar weather that flows from the star we call our Sun.